The sort operation arranges stack elements in some order. For example, consider the stack 11, 29, 5, 17. Here's the result of sorting the stack in ascending order. Sorting is one of the most useful collection operations. Here are some examples of problems that are solved by sorting. For instance, to help us find books at a library, sort the library books by title or the author's name. To find cheap sweaters, sort the sweaters by price in ascending order. And finally, to find the 5 tallest mountains in the world, sort the mountains by elevation in descending order. Next, let's discuss how sorting works. There are a great many ways to sort, but here is one simple way to sort in ascending order. Step 1. Write down an empty sorted stack, which will contain the numbers in order. Step 2. Find the maximum number in the original stack and pop it from the stack. Step 3. Push this maximum number into the sorted stack. Step 4. Repeat steps 2 and 3 until the original stack is empty. Let's use this algorithm to sort the stack 11, 29, 5, 17. Here's a video demonstration. We pop the maximum value and we push it to the sorted stack. And we repeat this process until all the elements are in the sorted stack. Here's the table view. In step 1, we popped 29 and pushed it into the sorted stack. In step 2, we pop 17 and push it to the sorted stack. In step 3, we pop 11 and push it to the sorted stack. Finally, in step 4, we pop 5 and push it to the sorted stack. As we can see, the result of sorting the stack 11, 29, 5, 17 is equal to the stack 5, 11, 17, 29. By repeatedly pushing the maximum value to an empty stack, we ended up with a stack that contains the smallest value at the top and the largest value at the bottom. This algorithm is called a selection sort. Now let's try to more precisely describe selection sort. We need to keep track of the sorted stack, so we first convert the sort operation to the sort compute function, whose input is the original stack and the current sorted stack, and the output is the fully sorted stack. We can convert the expression as follows. Result of sorting S is equal to the output of the function sort compute, where input stack is S and the sorted stack is empty. Next, suppose that variable max is equal to the maximum of the stack xy, and the variable idx is equal to the index of max in stack xy. Then the output of function sort compute, where input stack is stack xy and the sorted stack is c, is equal to the output of function sort compute, where input stack is result of removing index idx from stack xy and the sorted stack is max c. Notice that the stack is xy rather than a single variable. If the stack was a single variable, then the stack could be empty. But we want the stack to have at least one element, so we use a 2-element list. Also, notice that the maximum value is removed from the input stack and pushed into the sorted stack. The output of function sort compute, where the input stack is empty and sorted stack is C, is simply C. Let's use the above properties to evaluate the expression result of sorting stack 248, 2150, and 1400. First, we convert the expression to the sort compute function as follows. the result of sorting stack 248, 2150, and 1400 is equal to the output of the function sort compute, where input stack is 248, 2150, 1400, and the sorted stack is empty. Next, let max be equal to the maximum of the stack 248, 2150, 1400, and IDX be the index of max in the same stack. Then we claim that the output of function sort compute, where the input stack is 248, 2150, 1400, and the sorted stack is empty, is equal to the same function, where the input stack is the result of removing index IDX from the stack, and the sorted stack is the stack max. Since the maximum of the stack 248, 2150, and 1400 is equal to 2150, we claim that max is equal to 2150. And the index of 2150 in the stack is 1. So we conclude that IDX is equal to 1. Using substitution, we claim that the output of the function, where the input stack is the result of removing index IDX from the stack, and the sorted stack is stack max, is equal to the same function where IDX is replaced by 1 and max is replaced by 2150. We know that the result of removing index 1 from stack 248, 2150, 1400 is equal to the stack 248, 1400. Again, using substitution, we can replace the result of removing index 1 from stack 248, 2150, 1400 with the stack 248, 1400. Now we can begin another cycle. Let max be equal to the maximum of the stack 248, 1400, and IDX be equal to the index of max in the same stack. Then we claim that the function where input stack is 248, 1400, and the sorted stack is the stack 2150, is equal to the same function where the input stack is the result of removing index IDX from stack 248, 1400, and the sorted stack is the stack max 2150. We know that the maximum of stack 248, 1400 is equal to 1400, so we conclude that max is equal to 1400. Then we claim that the index of max in the same stack is 1. Therefore, IDX is equal to 1. Using substitution, we can replace IDX with 1 and max with 1400. We also know that the result of removing index 1 from stack 248, 1400 is equal to the stack 248. Then we can replace the result of removing index 1 from stack 248, 1400 with the stack 248. There's just one more element left. Since there is just one element left, we can just pop it and push it into the sorted stack. But since we did not specify such a property, let's go ahead and use the sorting property again. Let max be the maximum of stack 248, and IDX be the index of max in stack 248. Then we claim that the output of the function where the input stack is 248, and the sorted stack is 1400, 2150, is equal to the same function where the input stack is the result of removing index IDX from stack 248, and the sorted stack is max 1400, 2150. Since there is just one element, we're going to skip a few steps and make the following claims. Max is equal to 248. IDX is 0. The result of removing index IDX from the stack 248 is the empty stack. and the stack max 1400 2150 is equal to the stack 248 1400 2150. Using substitution, we can replace the result of removing index IDX from stack 248 with the empty stack, and max with 248. Then we claim that the output of function sort compute, where input stack is empty, and the sorted stack is 248 1400 2150, is equal to the stack 248 1400 2150. Now use the transitive property several times to conclude that the result of sorting stack 248 2150 and 1400 is equal to the stack 248 1400 2150. Notice that when we sort a collection in increasing order, the first element in the collection is the minimum value, and the last element in the collection is the maximum value. Thus, when we sort, we get the minimum and maximum values for free. But the sort operation requires more time to compute than the minimum or maximum operations, because the sort operation consists of many maximum operations. Thus, we usually don't sort just to find the minimum or maximum value.